Okay, so pretty much all of your homework grades should be in now. I did a lot of grading over the weekend, so grades for homeworks 1 through 4 should be in now. So you should have a pretty good idea of where your grade is sitting. I also graded, hold on, let me turn this off real quick. Okay. I also graded your exams over the weekend. I still need to enter those. Those will be uploaded by the end of the day today, if not at the absolute latest by class tomorrow, with all of your comments and everything. These ones went extremely well. So yay. But good. Are there any questions on anything? The new Alex module should start. I believe the one that is open today is intro inverse trig functions. After today, you should be able to complete that module in its entirety. If not, be able to start just the inverse trig functions module as well, which is the next one. So keep an eye out for that. I will have homework 5 posted by the end of the day today, if not very early on tomorrow. So we're in the home stretch, only 2 more weeks. All right, if there's no questions, we'll go ahead and get started. Okay, so I will share screen. Okay, so we ended the last unit with pretty much just doing a bunch of trigonometric proofs using those identities and solving trigonometric equations. We're still going to keep doing a little bit more of that second thing, solving trig equation, but we're going to change the context completely for a bit. This last unit focuses on 3 things mainly, and it's inverse trig functions, which is the first thing we're going to look at. Solving these with using inverses and doing applications of that. Then we're going to do something called solving triangles, which is, okay, how can we use things like sine, cosine, and tangent to solve triangles that are not right triangles? And can we even do that? And then finally, looking at things called vectors and polar coordinates. But first, we're just going to start off with inverse trig functions for the first couple of days. And if you remember from college algebra, inverse trig functions are very similar to just inverse functions in general. Instead of taking the thing we would normally put in and getting something out, we would take the thing we would normally get out and put it in. So what does that mean in the context of trig exactly? Well, we know from what we have been doing all semester that if we put in an angle theta into the sine function, we get out the y coordinate on the unit circle. If we put in an angle theta into the cosine function, we get out its x coordinate on the unit circle. And if we put theta into the tangent function, we get y over x, which if you remember at the beginning of the semester, y over x is essentially just rise over run. We can interpret this tangent value as a slope, which we would usually denote m, as in the form y equals mx plus b, that form of a line where m was the slope and b was the vertical shift. That is how the standard forward direction, not inverse trig functions work. But what if we want to invert them? What if we want to think about going the opposite direction? Well, first of all, just for notation, we denote this one of 2 ways. We call it sine to the -1, which is sine inverse. We also write arc sine. If you see either of these 2 things, they mean the exact same thing. If you see sine inverse, cosine inverse, tan inverse, or arc sine, arc cosine, arc tangent, those all mean the exact same thing. There's no difference between this and this, or this and this, etc. So how do these functions work? Well, if you remember inverse functions, essentially you're swapping the output in the input values. So instead of putting in an angle theta, putting in an angle theta to the sine function and getting out a y coordinate, we put in a y coordinate and we get theta back. Similarly, we put in an x coordinate to the inverse cosine function, because that is what the cosine function spits out, and we get an angle back. We put in a slope to the tangent function, i.e. the slope of this line here on our unit circle, and we get back the angle. Pretty much how inverse functions have always worked in college algebra or any other context. This is just different with trig. If you remember the fancy vocabulary from the beginning of the semester, abyssa is just the really fancy word for x coordinate on the unit circle. and ordinate is just a really fancy math word for y-coordinate on the unit circle. So what is this little diagram at the bottom saying here? It's okay, well, both into the cosine, sine, and tangent function, we put in an angle theta, and it gives us three different things. If we put the angle into the cosine function, we get the x-coordinate. If we put the angle into the sine function, we get the y-coordinate. And if we put the angle into the tangent function, it gives us the slope of y over x. Cool. So the inverse functions, as you can see, have the exact opposite operation. Instead of the angle all being over here, the angle is always the output. Instead of the angle always being the input, it's always the output. And so we have to be very careful with what we're putting in and identifying and knowing exactly what kind of thing we're feeding to a function. Because we're so used to feeding angles to trig functions, it is immediately intuitive to just think, oh, it's an input, it's an angle. No, depending on which inverse trig function we're using, we have to be sure to think about, okay, I'm working with arc cosine. My input, therefore, is an x-coordinate because the cosine function gives us an x-coordinate. So with arc cosine, the input is always an x-coordinate on the unit circle. With arc sine, the input is always a y-coordinate on the unit circle. And with arc tangent, the input is always the slope of the x and the y coordinate. We think of tangent as the slope of that coordinate. Questions on this idea? Okay, let's just do a little bit of practice, just getting comfortable calculating these, and then we will move on to talk about some more conceptual ideas with it. So we just want to use a calculator to evaluate these following three things. You can follow along if you want. That's fine by all means. It's helpful to see what happens. So your calculators, I don't know if scientific calculators do, I believe they do, but for sure, if you have a graphing calculator, there should be a sine, cosine, and tangent inverse button. We just want to use that to evaluate tangent inverse in degrees. So putting the calculator in degree mode and evaluating tangent inverse of this, we get negative 39.69 degrees. Cool, that worked nicely. If we do the same thing, put our calculators into radian mode and evaluate sine inverse, it gives us 1.25 degrees or 1.25 radians, it's in radians. Okay, let's stop and think for a minute. We know I'm getting this out in degrees and this in radians because it's basically telling me that's what's going to happen. This is going to give me a degree value and this is going to give me a radian value. Cool. But from the last slide, what is this number and what is this number? Because normally we just intuitively be like, yep, that's an angle in radians because that's what we're used to putting in trig functions, but it's not. Because this is a tangent, this is the input for an inverse tangent, we have to remember and we have to keep track of the fact that this is a slope. And because this is going into the sine inverse function, this is a y coordinate on the unit circle. Okay, so then this would be an x coordinate on the unit circle. Now, this should raise a red flag here. And if it doesn't right away, we'll see why in a minute, but try to type this into your calculator. See if cosine inverse of 1.26, what does it give us? Well, I typed it into my calculator and it gave me something called a domain error. It may just say error. Your calculator may be fancy enough to say domain error. Either way, your calculator will not be able to evaluate this. And why is that? Well, if we remember, here's our little unit circle. It's very little. We want this right here is an input. This is the x coordinate on the unit circle. And if we remember, let's just talk about that coordinate right here. That coordinate is 1, 0. We cannot get x coordinates on our unit circle larger than 1 because the unit circle by definition has a radius of 1. So if you remember, values of sine and cosine will never be greater than 1. So of course that trying to put that into the inverse cosine function gave us an error because there is no angle theta whose cosine is 1.26. It doesn't exist. Your calculator will not be able to do it. It cannot take values greater than 1. So that will always return an error. So that raises the question, what is the domain of arc cosine, arc sine, and arc tangent? i.e., what kinds of values can we put into this function? Well, as we kind of already talked about, with cosine, We can never get x coordinates greater than 1. And we can never get x coordinates less than -1. We're always bound by that radius of 1 of the unit circle. So the domain for arc cosine is just -1 to 1. And if you remember from college algebra, those square brackets mean that it includes -1 and includes 1. That's how we write that. Similarly, let's think about the domain for arc sine. Well, we can't get a sine value any greater than 1 because the y coordinate on the unit circle will never be greater than 1. We also cannot get a sine value less than -1 because, again, we are bound by that radius of 1. The unit circle, we can't go any further than 1 for y coordinates either because the radius of the circle is 1. So the domain for arc sine is also just -1 to 1. We can land anywhere between -1 and 1, just going along this circle somehow, but we will never be able to go beyond -1 or 1. Any questions? Okay, what about arctangent? Well, let's think about conceptually what arctangent is. Arctangent, if we're thinking about the unit circle, is a slope. It is the slope of the y coordinate and the x coordinate. Let's say that our angle is just right here. This leaves us with a really long x coordinate. Let's say the x coordinate is like 0.99 and the y coordinate, let's just say, is 0.01. If we do that division, that's going to give us a really small number. Similarly, what if we have an angle like right here, where the y coordinate is 0.99 and the x coordinate is 0.01? If you try putting that in your calculator, that's going to give us a really big number. So it turns out that we can push these to the extremes in either direction, and we can actually get any slope. The slope is not bound because of the radius. We can get a line of any slope, because here's the line with slope 0. And this line is too big to have any slope. That slope does not exist. It's a vertical line. We can't find the slope of that. But if we go just a touch past that, we could make a slope as large as we want. So the domain for arctangent is -infinity to infinity. And if you remember, this is just the notation for pretty much. You can just think of that as being everything. And again, we have instead of the brackets at the end, we have open parentheses because you can never reach infinity. That's a math technicality. But in case you're wondering, that's why we use circle parentheses there. But the domain for arctangent is all of the numbers. It's everything, -infinity to infinity. But arc cosine and arc sine are restricted from -1 to 1 because the inputs are x coordinates and y coordinates on the unit circle respectively. And if it's not an x or a y coordinate on the unit circle, it's not going to give us an answer. It's not going to give us an angle. Questions on that? All right, let's see if we can use inverses to solve something. Here's this little triangle. It's a right triangle, so we're still in nice right triangle land. I want to find x and round my answer to the nearest degree. Okay, so in the past, I would have asked you to find something like the cosine of x or the sine of x or the tangent of x, which you all could have done. You would immediately know, okay, I would need to solve for this third side of the triangle, use Pythagorean theorem, and then use whatever trig ratio fits into the part of SOHCAHTOA I need, and then boom, we're done. But now I want you to actually find the angle x. So how could we do this? Well, what information do we know? We know the side opposite of x, and we know the hypotenuse of the triangle. So opposite hypotenuse, I think we should try to use the sine function. So I know that the sine of our angle x is 7/13. And that's something you've done before. You know that that's just how sines work, SOHCAHTOA. Okay, but we want to get x by itself. This isn't a familiar angle on the unit circle, so I can't do what we did in our last unit and think about, okay, what angle's x, make a sine of 7/13. We don't know this angle. However, we have a new tool called the inverse function. And if you remember, inverse functions kind of undo each other. They unwrap each other like a present. So what we can do is apply the sine inverse function to both sides and see what happens. So what I mean by that is we want to take the sine inverse of both sides of the equation. If you remember from college algebra, for example, like x to the third and third root of x were inverses of each other. So when you took, for example, one of like, if you took the inverse of that, that would just give you x. And if you took x to the third root of x to the third, that would also just give you x. It's not as easy to see why it works here, but all inverses essentially just unwrap each other. And we'll explain more how that works with trig functions in a minute. But if you just remember from algebra, that's kind of what's doing. One undoes the other in a sense. So sine inverse applied to the sine undoes that. So we're just left with x is equal to sine inverse of 7/13. And now we are good to plug this in our calculator. And if our calculator is in degree mode, because we need it to be because it asked for nearest degree, again, our default is radians for this class, but it asks for degrees, so we need to give it that. We would get to the nearest degree that x is 33 degrees, which intuitive check, we know that there are no angles greater than 90 degrees in this triangle because it's a right triangle and that one's 90 degrees. These two will be less. Okay, we got an angle between 0 and 90. Cool, we're good. Questions on how we did this one? Okay, let's do one more and then we'll kind of unwrap this idea of inverses undoing each other. So I have an airplane. The plane is 108 miles north and 176 miles east of an airport. I want to find x, i.e. the angle the pilot should turn in order to fly directly to the airport. Okay, here's x. I have the side opposite of it. I have the side adjacent to it. SOHCAHTOA. Tangent is opposite over adjacent. Perfect. I think I should use the tangent function. So I don't know x, but I know that the tangent of x is equal to the length of the opposite side, which is 108, over the length of the adjacent side, which is 176. I want to get x by itself, and 108 over 176 is not a nice angle on my unit circle. I can't just look at it and think, what angles x do I know that have a tangent of 108 over, you can't think about it. It's not a nice angle. We don't really know how to think about it. So we have to use the inverse function, this new tool we have. So taking the tangent inverse of both sides, trying to unwrap this, we get that the tangent inverse of the tangent of x is equal to the inverse tangent of 108 over 176. Inverse tangent undoes tangent. So we're just left with x is equal to inverse tangent of 108 over 176. And then plugging this into my calculator, I recognize that this angle is 31.53 degrees, or if I want it in radians, 0.55 radians. Questions on this one? Again, intuitive check, our answer makes sense. This angle has to be between 0 and 90 degrees because we are working with a physical triangle. We are not working on the unit circle. We can't think about 210 degree angles in the context of a triangle, but luckily we didn't get one of those. Okay, so now let's think about some inverse functions we're familiar with from college algebra to kind of help us get a conceptual understanding of what's going on with these trig inverse functions. So this one should be an old friend from college algebra that I just brought up. We have the pair of functions f of x equals the third root of x and g of x equals x to the third. These two do happen to be inverses, and we will see why. So let's start with trying to evaluate these things down here. I want f of g of -2. If we remember inverse function, when we have compositions of functions like this, we start on the inside and we work our way out. We can figure out what the thing on the inside is, and then we work our way out. We unwrap the present from the inside, which is a little counterintuitive, but then we get our answer. So let's ignore the fact that the f is there for now and just focus on finding g of -2. Well, when we input -2 into g, which the red function is g of x and the blue function is f of x, g of -2 gets us out -8. So now we've solved what g of -2 is, and we're just looking for f of -8, which just happens to be -2, because when we input -8 into f of x, we get -2 back out. Cool. What if we tried to go the other way? We do g of f of -2. Well, let's just focus on the f of -2 in the input first. F of -2, I don't really know what that is, but I know it's going to give me something probably around here. And then when I put it back into g, it's just going to give me that back, because again, these are inverses, they unwrap each other. So it will give us back -2. And if we can't see it on the graph, we can think about it computationally, because g of f of -2, f of -2 is just the third root of 2. So this is just g of the third root of -2, which is just the third root of -2 to the third, which you can see why the third root and raising something to the third power undo each other. So we're just going to get -2 back. Again, we can't see that graphically as nicely because who the heck knows what the third root of -2 is. It's not a nice point labeled on the graph, but you can check computationally. It still works. They're inverses. That's how inverses work. They unwrap each other. So in general, because they are inverses, regardless of what x we put in here, if we compose that function with its inverse, it's just going to give us x back. Same thing if we go the other direction, it is just going to give us x back. Essentially, the key kind of slogan for inverses to remember is that inverse functions undo each other. No matter what x value we put in, no matter what values for x, we could use 2,427,000,000. It would give us 2,427,000,000 back. Throughout the entire domain of both of these functions, they are inverses of each other. It works out really nicely. All right, let's consider another pair of inverses I'm sure you're even more familiar with from college algebra, which is square root of x and x squared. And I say pair of inverses cautiously, and you'll see why. So let's try to do the exact same process we did with the last one and see what happens. F of g of -2. Well, let's start with the inside. G of -2. This function right here is g of x. This one is f of x. G of -2 is 4, which makes sense. -2 squared is 4. So we're looking for f of 4. Well, we have f of 4 labeled right here, and f of 4 is 2. That's not what I wanted. That's the negative of it. I don't know what happened. Let's see what happens if we try to go the other way. Maybe it'll fix it. I want g of f of -2. That's not labeled on the graph, so let's do it computationally. F of -2, just plugging -2 into f, is just g of the square root of -2. We can't do square roots of negative numbers. If you remember, again, from college algebra, I know I'm bringing that up a lot, but the domain of square root functions, we cannot put negative values into a square root function. We cannot have a negative under the radical. It's a no-no. It doesn't work in the real numbers, which is what we're working in. So this, unfortunately, even though it was bad, we got the wrong answer up here. This made it worse because this does not exist. Now, why does this happen? Well, it seems like these two should be inverses, because if I take the square root of something squared, it should just give me the thing back, right? Well, no, it doesn't work because we can't take the square root of everything. We can't take the square root of negative numbers in math. So these functions are inverses, but only sometimes. In fact, these functions are inverses precisely when the square root of x is defined. i.e., on the interval 0, because the square root of 0 is 0, that is included through all the positive real numbers, 0 to infinity. So f of g of x equals x only from 0 to infinity, and g of f of x equals x, again, only from 0 to infinity. And f of g of x is equal to negative x from negative infinity through all the negative numbers, and then this does not exist through the negative numbers. Again, we don't care about this part of the domain as much because when we're considering the inverse of x squared, we don't care about the part where it doesn't work. We don't care about this. I just wrote that to be like, hey, this is what actually happens. We don't care about the behavior when it's not the inverse. We only care about the behavior when it is the inverse, which is from 0 to infinity. So x squared has an inverse, but only on a restricted domain. And we want to keep that idea in mind to think about when we're looking at trig functions, because the same issue kind of comes up. Well, how does that happen? Well, let's think about what would happen with restricting the domain of sine and cosine. If you remember, for something to be considered a function, just in general, we do something called the vertical line test, i.e., if we take a vertical line and just move it across our function, the function can only cross the vertical line at one point, no matter where we are moving the vertical line. Similarly, we have something called the horizontal line test, which is, okay, inputs and outputs are swapped pretty much for trig functions. I mean, not trig functions, for inverse functions. So instead of the vertical line test, we use the horizontal line test, i.e., is there any, if the inverse is defined, we cannot have the function crossing the horizontal line at more than one point at any time. Clearly, that does not work for sine. Here's a horizontal line. Wow, the function crosses at 1, 2, 3, 4 different points, and that's only in the part of the graph we can see. If you recall, it actually just passes at infinitely many points. We just haven't drawn them. So sine does not have an inverse. Sine theta itself does not have an inverse. And that kind of seems like it contradicts what we've been talking about. Like, what are you talking about? We've just been working with the inverse of sine for the last few slides. We've actually been working with an inverse that has a restricted domain. And we'll see how that works in a second. But sine itself does not have an inverse, nor does cosine, for the same exact reason. Think about it. If, for example, I want to find inverse sine of 1/2. Because I'm working with a function, I should only have one output. What's an angle who has the sine of 1/2? Well, we did a lot of this in the last unit. Let's think about it. Okay, so sine inverse equals 1/2 would imply that the sine of x is equal to 1/2. Well, that means that x could equal pi over 6. Pi over 6 has a sine of 1/2, but so does 5 pi over 6. So does 13 pi over 6, 17 pi over 6, etc. And if you remember, we denoted this kind of forever continuation. We had the plus 2 pi k. And that was to indicate at that time that there were infinitely many solutions to this. And at the time, we were just treating them as equations. We just wanted to find when the sine of x was equal to 1/2. We didn't care about this inverse function. We didn't want that to be a function. We just wanted to find all the possible places where the sine of x was 1/2. So it was okay that there were infinitely many solutions. But if we want this to be a function, we need x equals sine inverse of 1/2 to only have one output. So how should we restrict the domain? Well, mathematically, there is a standard part of the domain we used to restrict to, and it is from here to here. We use that little principal chunk of the sine function as our restricted domain for when working on the inverses, and that happens to be from -pi/2 to pi/2. Notice that this makes it past the horizontal line test. There is at no point on this portion of the graph can I draw a horizontal line such that it crosses more than one point of the graph. We go from our little high peak up here to our low peak down here. Also notice that this goes from -1 to 1. So all possible values for sine, all of values from -1 to 1 are in there. So it covers pretty much everything we need just in that little restricted domain. So what does that mean? Well, that means all of the outputs for our inverse function are going to be within -pi/2 to pi/2, and we'll talk about that in a second. But we can also restrict cosine theta similarly, except we don't do -pi/2 to pi/2 because then that gives us that, which, wow, that doesn't pass the horizontal line test. So instead for cosine, it is standard to go from here to here, which is 0 to pi. So if we restrict the domain of the sine and cosine functions to just looking at these much, much, much smaller domains, these parts of the domains of the sine and cosine function do have inverses. The inverse function just looking from -pi/2 to pi/2 and for sine and 0 to pi for cosine do allow us to have inverses. No matter what input we put, there will only be one output because it passes the horizontal line test. Questions on that one? All right, similarly, tangent, we can think about, okay, does this pass the horizontal line test as is? No, we cross here, 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 etc. And again, that's only the part of the domain that we drew on this graph. It passes at infinitely many points, so we need to restrict it to an interval. What's typical, what's standard in mathematics is we restrict it to this principal interval right here. That's actually the principal interval we used for graphing, which is nice enough, which is -pi/2 to pi/2. Again, we will never be able to get something on the asymptotes themselves because they're asymptotes by definition. There's no output of the tangent function on pi/2 or -pi/2. If we plug those two things into the tangent function, we get undefined. So that's why we have the round parentheses at the end. So that is the restricted domain of tangent we look at in order to get an inverse. Okay, so now that we have the domains of the functions we are going to look at, let's think about the range of the inverse. So if you remember, inverse functions, we're just swapping inputs and outputs. That's all we're doing. So just going to make a note of that at the top. Inverse inputs and outputs are swapped. So what does that mean? Well, that means that the range of the inverse, i.e. the range of the y values, is the domain, i.e. the space for the x values of the original function, because we're just swapping x's and y's. So the x's, which define the domain of the original function, become the y's of the inverse, which define the range of the inverse function. So as a result, the range of arcsine, i.e. the y values for arcsine, are -pi/2 to pi/2. i.e. for any y value on the unit circle that we put into the arcsine function, it will give us an angle, if we remember these are angles and radians, between -pi/2 and pi/2. So I like pictures, let's draw a picture of this as we go. So -pi/2 to pi/2, that means that all of the values for arcsine, whatever y coordinate we put in there, will get an angle over here. Because if we remember, this is 0, this is pi/2, pi, and I'm just going to label this as -pi/2 for now. It's also 3 pi/2, but if we're thinking about going negative angles, this is -pi/2 to pi/2. So that is the range for arc sine. We will always get outputs in those two coordinate, or not coordinates, quadrants. Range of arc cosine is 0 to pi because the domain of the restricted cosine function is 0 to pi. So that means whatever x coordinate we plug in to x coordinate from the unit circle, we plug into the inverse cosine function, we will get an output, we will get an angle over here. So that is our range for arc cosine. And then finally, arc tangent is also negative pi over 2 to pi over 2, except like this. It's green. So those also all lie in this region here. Whatever angle or whatever slope we plug into our tangent function, whatever y over x, it will give us an angle from negative pi over 2 to pi over 2 as an output. And we can see that in the diagram. So what does this mean essentially? Well, it means that you will even, so for example, sine of 1/2, or sine of x equals 1/2. We know that means x could equal pi over 6, right? Cool, that is in the first quadrant. We could get that, we would get that as our output, but it's also equal to 5 pi over 6. However, 5 pi over 6 is not in that range. So if we tried to do the sine inverse of negative 1/2, it would never give us 5 pi over 6. 5 pi over 6 is not within the range for arc sine. It would never give us 5 pi over 6. 5 pi over 6 is technically a solution to sine of x equals 1/2, and we'll need to address this kind of discrepancy later. However, the inverse function will never, ever, ever give us 5 pi over 6 because we had to restrict the domain in order to make sine inverse a function. So it will only ever give us, if we plug in sine inverse of 1/2, it will give us pi over 6 back because that is in quadrant 1. And we'll talk about that conceptual idea a little bit more in a second. But for now, are there any questions? Keep this picture in mind. It'll be helpful. And yeah, let's try to use this a little bit. So I want to use the information I just talked about to evaluate these three exactly. Now, what does evaluate exactly mean? That means don't plug it into your calculator. Whenever you see the words exactly or give the exact answer, that means I want things in terms of pi's and square roots. So let's think about these. I want to evaluate the arc cosine of negative root 2 over 2. Well, remember this negative root 2 over 2, we're inputting it into the arc cosine function. So what is that negative root 2 over 2? It's an x coordinate on the unit circle. So let's draw this out. If we remember from the last slide, what are my possible output values for the arc cosine function? Well, they're from 0 to pi. They're where this red area is shaded. So I know that my output, no matter for whatever this input is, it's going to be somewhere up here. Okay, now I know I'm working with an x coordinate on the unit circle of negative root 2 over 2. Where in my little shaded region do I have an x coordinate of root 2 over 2 or negative root 2 over 2? Well, my x's are negative on this side. So this is my angle right here. This is the only angle in my shaded region that has an x coordinate of negative root 2 over 2. And it happens to be 3 pi fourths. So your answer to this one is 3 pi fourths. Again, there's another angle that has a cosine of negative root 2 over 2, and that's down here, and that is 5 pi fourths. However, that is not a possible output. That is not in the range of our arc cosine function. So we don't think about 5 pi fourths. It's not in the range. We're not talking about solving an equation. We're talking about what is the inverse function output given a specific input. And so we have to consider the range, which is why the only solution is 3 pi fourths. Questions? All right, let's do another one. Sine inverse of -1/2. Well, we know that the answer for this one is in the interval -π/2 to π/2, because that's the range for our sine inverse function. So let's just draw that little diagram. -π/2 to π/2 is this area over here. So we know that our answer is going to be in that shaded region. Cool. What is this guy right here? -1/2. It's an input to the inverse sine function. That is a y coordinate on the unit circle, because it's going into inverse sine. We have to think about which inverse trig function we're using. They're not all just angles anymore. So I want to think about, okay, where in my shaded region do I have a y coordinate on the unit circle of -1/2? What angle in the shaded region has a y coordinate on the unit circle of -1/2? Well, here's the y-axis, y's are negative down here. And I have, so -1/2 is about right there. And if we remember, that angle, if we're going clockwise, is 11π/6, or counterclockwise. If we're thinking about positive angles, that angle is 11π/6. Cool. But my answer is going to be from -π/2 to π/2. My calculator, if I plug this into my calculator, is not going to spit out 11π/6. What is it going to spit out? Well, my answer needs to be in -π/2 to π/2. So I probably need to think about going, taking a negative angle, and that is just -π/6, which makes sense. We need 12π/6 to go around the full unit circle. Going the positive angle direction, we get 11π/6 of the way there. So there's a remaining π/6 there. Questions on that? All right, let's think about one more. Arctangent of -1. The answer for this one will also be in -π/2 to π/2, because we're working with the arctangent function, and the range of arctangent is -π/2 to π/2. So one more time, let's draw ourselves a little picture to help us when we're trying to find the angle. I will use green this time. -π/2 to π/2. Cool. Okay. Now I need to think about where in these quadrants does the tangent function evaluate to -1, i.e., what angle in these two quadrants gives us a tangent of -1, i.e., a slope of -1, i.e., probably the same thing over the same thing but negated. Well, that happens with √2/2 over -√2/2. That angle is precisely right here. Again, we traditionally think about going the positive direction around, giving us 7π/4, but our answer needs to be in -π/2 to π/2, because we're thinking about the range of the inverse trig function, so we can only think about the restricted domain of the trig function. So this angle is going to be the answer instead, and that is -π/4. As a guide, when we're doing these, there's two questions we should be asking ourselves. The first one is, in what quadrants does blank exist? In what quadrants does arc cosine exist? In what quadrants does arctangent, arcsine exist? What is the range? What are the possible output values of this function, and what quadrants are we considering? And those are the quadrants I colored in just to give us a little guide when we were thinking about it. And then once we have those quadrants, we want to think about where in these quadrants, or where in this region, does blank evaluate to blank. What do I mean by that? Where in these quadrants does the tangent function, for example, evaluate to -1? Where in these quadrants does the sine function evaluate to -1/2? You can also think about where in these quadrants Is there an angle theta whose sine is -1/2, or whose y coordinate on the unit circle is -1/2? Just if you're asking yourself these two questions or different wordings of them, that is the process you should be going through when answering these kinds of questions. They're very similar to what we've already done thinking about solving trigonometric equations, only difference now being we have restricted ranges, we have restricted domains of inputs, so the ranges of our inverses are going to be restricted because otherwise the inverse would not exist. So all we have to do is make sure to restrict our range appropriately and then evaluate. Questions on this? Let's think about a couple more. Instead of just doing these, let's think about composing these kinds of functions. Composing them with their inverse, to be specific. So let's start off with this one. I want to find the arctangent of the tangent of -π/4. Now, if you remember when we did these with the triangles, they just kind of unraveled themselves really nicely. And the reason for that, if you look back at this diagram up here, is that all three of our inverse trig functions, sine, cosine, and tangent, are defined in quadrant 1. And when we're working with triangles, we're only working in quadrant 1 because we're never going to have an angle bigger than 90 degrees, i.e. we're never going to have an angle bigger than π/2 radians. So when we're working with triangles, that unwrapping will always work. However, when we're working with the entire unit circle and working with the entire 2π radians, we have to be a bit more careful. These don't always just unwrap each other. So let's think about the first one, arctangent of tangent of -π/4. The answer to this one is just -π/4. Why is that? Well, -π/4 is an angle that is in the range of -π/2 to π/2. It is in the range of the inverse function, i.e. it is within the restricted domain of the input functions. So the inverse for tangent is defined right here because -π/4 is within -π/2 to π/2. So the inverse is defined, so it works as we'd expect it to. They just unwrap each other and we're left with -π/4. Cool. That's not how that always works. Let's think about the cosine of -π/3. If we remember the restricted domain for cosine, i.e. the range for arc cosine is 0 to pi, clearly -π/3 is not within that scope. So what do? Well, the other way we've thought about doing inverse functions is starting on the inside, just evaluating the thing we have on the inside, and then working inside out. Let's see if that works here. I just want to find first the cosine of -π/3. Something I've done before, it's something I'm comfortable with. So let's do that. Here is the angle -π/3. And if we recall, remembering our unit circle, this is 1/2 (-√3/2). My cosine is my x-coordinate on the unit circle. So cosine of -π/3 is 1/2. So I will replace that with 1/2. Okay, now I'm left with this arc cosine of 1/2. So what do I have to think about? What questions am I supposed to ask? Well, if you remember from the last slide, I want to think about what angle in the range of arc sine or arc cosine, I meant, has cosine of 1/2. So now this is just like one of the problems we did on the last slide. What is my range for arc cosine? Well, I wrote it right here. It's 0 to pi. So we are only considering things in this region right here. Now, what angle in this region has a cosine of 1/2, i.e. what angle in this region has an x-coordinate on the unit circle of 1/2? Well, we know it's not -π/3 because this is not in our shaded region, but we do have an angle with a cosine of 1/2 in our shaded region, and it's right here. And this angle just happens to be 1/2, or the coordinates are 1/2 root 3 over 2, but the angle is pi thirds. So pi thirds is our final answer. It is a little bit coincidence that it's just the negative of negative pi over thirds, but it worked out nicely. And we can see why. The other angle was down here. They shared a cosine. They shared this length of 1/2 right here. So instead of going the negative direction, pi thirds, we went the positive direction, pi thirds, and that's how that worked out. So this one, we couldn't just say, oh, those two cancel and we get negative pi over thirds. That is because cosine does not have an inverse at the angle negative pi thirds. Our function cosine does not have an inverse. We can't do it there. We have to restrict the domain. We can only accept inputs of 0 to pi for cosine to have an inverse. So those two couldn't just unwrap each other. We had to evaluate the inside function and then think about, okay, the cosine of negative pi thirds is 1/2. Let me look at my range for arc cosine. What angle has an x coordinate in my restricted domain of 1/2? Questions on that? Okay, let's do another one. Let's think about, okay, this one was nice because we know the cosine of negative pi thirds. It worked out for us really nicely. But what happens when we're working with an angle that we can't just evaluate step by step? What if we have something we don't know the answer to, like negative 10 pi sevenths, for example? So I want to unwrap sine inverse of the sine of negative 10 pi sevenths. Well, I know that sine function has an inverse from negative pi over 2 to pi over 2. Negative 10 pi sevenths is not in that domain. Negative 3.5 pi sevenths is the equivalent of negative pi over 2, and this is clearly larger than that. So these two functions don't unwrap each other because sine does not have a defined inverse at this point. So we need to do some extra work. I don't really know what to do here because I don't know how to evaluate negative 10 pi sevenths. So I'm going to draw a picture because drawing a picture always helps. Okay, here's my axes. And I know that the sine function, or the inverse sine, is defined here. So I'm just going to shade that in now. Now, where is negative 10 pi sevenths? Well, if I go around this way, negative direction, that is 7 pi sevenths. And if you think about it, it's going to land in quadrant 2. It's not quite to this point because that would be negative 11.5 pi sevenths, I believe, or negative 10.5 sevenths. So we're not quite there. We land in quadrant 3. So here's our angle. Let's call this negative 10 pi sevenths. Again, we don't need to know exactly what it looks like. All that's important is what quadrant does it lie in. That's all we care about. Where do we land? Well, we didn't land where we wanted to. We didn't land in quadrant 1 or quadrant 4 like we needed. So as we expected, we need to do some extra work. Now I want to think about, okay, what angle in my allowed range over here, in my restricted domain for sine, has the same sign as negative 10 pi sevenths. Remember, sine is the y coordinate on the unit circle. So I want something I'll just do that in a different color. I want something in my allowed range, in my restricted domain of sine, that has that same sign. I want something in my restricted domain that has that also crosses that pink line, that has the exact same sign. So that would be this angle right here. Still has radius 1 because we're on the unit circle. If we think about, we have some circle like this. We want this point over here. It has the same y coordinate. This y coordinate here and this y coordinate here are equal. So we want to find this angle. We want to find whatever this guy is. Questions on that? Okay. Now that we've identified what we want, the tricky part is, how the heck do we find this angle? What is it? Well, this isn't always going to be the case, but let's think about it geometrically. We knew that going halfway around like this was 7 pi over 7, and then we went 3 pi over 7 more to get to negative 10 pi over 7. 3 pi over 7 was the reference angle. So we know that our answer right here is this angle. What is this angle? Well, in this case, it happens to be the reference angle because this angle right here is 3 pi sevenths above the x-axis. It was raised 3 pi sevenths radians above the x-axis. So is this one. So they're at the same exact y-coordinate. So the answer for this one does happen to be the reference angle, 3 pi sevenths. Just by thinking about, okay, where do they cross the y, this y coordinate, where does that occur? Where are they the same? And that happens to be, in the case of this sine function, the reference angle. That won't always be the case. You have to draw a picture. Sometimes it's a negative reference angle. We have to think about it because sometimes we're going to end up with something down here in the fourth quadrant, and reference angles are always positive. So we have to think about adjustments sometimes. But the adjustment we had to make for this one is, okay, I want something with the same sign, i.e. the same x coordinate. How can I do that? Questions? And again, we'll get more examples with this. This probably seems pretty uncomfy just first looking at it, but we'll get more practice and things may start to make a bit more sense. Okay, now let's think about the last one, tangent inverse of tangent of 5 pi over 6. Well, we know that the tangent has an inverse defined from negative pi over 2 to pi over 2. Is 5 pi over 6 in that domain? Nope. So we're going to have to do a little bit of work. We could do it either way with this one. I'll show it either way. We could either do it by evaluation, unwrapping from the inside out because we know the tangent of 5 pi over 6, or we could do the reference angle way that we just did with sine, which I will do that too, just so we can see another example of that. But let's start with evaluation. What is the tangent of 5 pi 6? Well, 5 pi 6 is right here. Its sine is positive 1/2 and its cosine is negative root 3 over 2. So the tangent of 5 pi 6 is 1 over negative root 3, which normally I would rationalize, but I'm not going to bother because this is not my final answer. Okay, now where in my allowed range of values for the inverse function, i.e. this little range over here, do I also have a tangent of negative 1 over square root of 3? Well, because it's a negative tangent, it's going to be in the fourth quadrant because the first quadrant's only positive tangents. I want a sine of 1/2 or plus or minus 1/2 and a cosine of plus or minus root 3 over 2. That's going to happen at that angle right there, which is at negative pi over 6. Cool. How else could I do this? Well, I could also use the reference angle again. I could think about, okay, I need an angle. My reference angle right there is pi over 6, which we can calculate just by 6 pi over 6. The x-axis right here, minus 5 pi over 6 equals pi over 6. Cool, that's my reference angle, but I know I need a negative tangent. So the inverse tangent is going to be, it's plus or minus pi over 6 in some fashion, but I know it's negative because we have it's negative over here. So it's going to be negative pi over 6. This way is honestly much easier with evaluation because it's not precisely the reference angle, but if it helps you to think about it both ways, just as kind of an intuitive check, you can do it either way. Questions so far on this idea? Again, we're going to do a few more, so if they don't entirely make sense yet, that's okay. Okay, let's do a little bit of a summary of what we know so far with this idea of composition. When we're solving these problems, there's a couple questions we want to ask ourselves. First, we want to check, is the angle I am given in the range of the inverse function? So that check was basically up here when we were like, okay, negative pi over 4, is that in this range right here? If it is, cool, they just unwrap each other and we're done. If it's not, we have to do some conversion. Is this angle here in the range of my function? Yes, no, no. Okay, we have to do a little extra work. So that's just checking, is the angle that you're given in the inside function in the range of the inverse function? If it is, great. If not, we need to find the angle with the same function output that is in the correct range. That is where we would color in our correct range on the axes and think about, okay, I know that the sine of this angle that's not in there is 1/2. Where in my range is there an angle with a sine of 1/2? So we know that the sine function allows quadrant 1 and quadrant 4. So when we're given our theta in quadrant 1 and quadrant 4, we're golden. They just unwrap each other. However, what if we're given one in quadrant 2 or quadrant 3? Let's draw a picture. We know that here is where sine inverse is allowed, quadrant 1 and quadrant 4. This is the area we're allowed to have outputs of sine inverse. What if we're given a theta in quadrant 2? What if theta is given right here? Well, it turns out for sine that if theta is in quadrant 2, we're going to end up converting it to quadrant 1, which makes sense, right? It's exactly like this problem we did up here. We had a positive sign, we had to convert it to the quadrant with the positive sign we needed. So our quadrant 2 angle got moved to quadrant 1. Similarly, we have an angle with a negative sign down here in quadrant 3. Quadrant 3 is not allowed. What angle in our allowed range is going to have a negative sign? Quadrant 4. So those will always get converted like that. You can think about them getting moved like that. Similarly, we know that cosine is defined up here in this region. So if we're given angles in quadrant 1 and quadrant 2, we're golden. We don't have to do anything. What if we're given an angle in quadrant 3? Well, then that gets converted to quadrant 2, negative cosine to negative cosine. What if we're given an angle in quadrant 4, has a positive cosine, then we convert it to an angle with a positive cosine up here. So the sine ones just move laterally and the cosine ones just move upwards longitudinally. Okay, what about tangent? We know that tangent inverse of some slope is defined over here. Just coloring that in. We know it's defined over here. Neat. So if we're given angles in quadrant 1 or quadrant 4, we're good to go. We don't need to do any conversion. We can just let them unwrap each other and the answer is theta. Beautiful. But what if we're given something in quadrant 2 or quadrant 3? Well, if you recall in quadrant 2, the tangent of angles is negative because we're looking at a slope and we're looking at a positive y value divided by a negative x value. So we're going to end up with a negative slope. So we need to convert it to the quadrant that also has a negative slope. Quadrant 3 or quadrant 1 has a positive slope, so we don't move this way. But quadrant 4 has a negative slope because we're looking at a negative y value over a positive x value. So angles in quadrant 2 are going to get converted to quadrant 4. And then angles in quadrant 3 have a positive tangent because we're looking at a negative x and a negative y value. So those get converted to angles in our allowed range with a positive tangent, which is in quadrant 1. This picture doesn't help everyone, I understand that, but if you want just kind of like an idea for, okay, where am I going to end up if this kind of table helps you, you can think about sines just move laterally across, cosines just move longitudinally upwards, and then the tangents go crisscross. Okay, I think we have time for 1 or 2 more examples, but before I move on, are there any questions on this? Okay, let's do a couple more. These are a little bit different, but not too different. I want to find the exact value of these two functions. Cosine inverse of the cosine of 5 pi over, or of 6 pi fifths. Well, if you remember, the restricted domain of cosine, which has an inverse, is from 0 to pi. Is my input within 0 to pi? Nope, it's a little bit bigger than pi. What does this angle look like? Well, 6 pi fifths looks something like this. It's just a little bit past pi. So it looks something like that. Okay, that's not a nice angle on my unit circle, so I can't just evaluate the cosine of 6 pi fifths and move on, because then my answer wouldn't be exact. So I have to think about, okay, 0 to pi is my allowed range of output values for this inverse function, so that's up here. Now I have to think about, okay, what angle in that allowed region has the same x coordinate on the unit circle, i.e. cosine, as 6 pi fifths? Well, here's my x-axis, so here is my x coordinate. Think about my circle. That's a really bad circle. Oh, wow. Okay. Yeah, even Notability didn't like that circle. Okay. So there's my circle. I want to think about, okay, what angle over here in my allowed space shares that x coordinate, and that is right here. They have the same x coordinate on the unit circle. It's not drawn super to scale. I'm sorry about that, but I want to find this angle here. And again, we can think about the reference angle. Here, we went pi fifths past the x-axis to get to 6 pi fifths because we went 5 pi fifths, 6 pi fifths. So we had to go another pi fifths this way to get to that equivalent angle. Again, the drawing's not great. I apologize. So that angle there is pi fifths. So that means that this entire angle here is 5 pi fifths, just, pi radians. And then the reference angle is pi fifths. So to get this angle we want right here, we take 5 pi fifths minus that extra pi fifths. It's above the x-axis, and we get 4 pi fifths. Again, the key for these is just drawing a picture when you're not familiar with the angle, seeing what it looks like, and using the reference angle in some fashion to get the angle we want. All right, let's try another one. And why is this one down here a little bit different? Well, because we can't even think about, okay, do these two functions unwrap each other? Because there is no world where inverse tangent undoes sine. Inverse tangent undoes tangent sometimes if we have input values in the correct region, but there is no universe where inverse tangent undoes the sine function. So we have to think about it a little bit differently. This one I think is easiest to just evaluate working inside out because we know the sine of 3 pi over 2. We can draw our unit circle. 3 pi over 2 is right here. Oops, I did not draw that on the axis. 3 pi over 2 is right there. And what is the y coordinate of 3 pi over 2 on the unit circle? It's -1. So we're looking for inverse tangent of -1. Cool, we've completely got rid of the sine. We're just working with one function now. So now do we need to think about? Well, what is the possible output values for the inverse tangent function? It's -pi over 2 to pi over 2. Those are in here. Now I need to think about, okay, what angle in this region in -pi over 2 to pi over 2 gives us a tangent, i.e. a slope of -1? Well, that angle's right here at √2 over 2, -√2 over 2. That is the one angle in our restricted domain for tangent that gives us that. And that angle, again, if we think about going this way, is 7 pi over fourths. However, that's not from -pi over 2 to pi over 2. So we need to think about going clockwise instead. We need to think about the negative angle, which is just -pi fourths. Questions? Okay. I think this is a good stopping place for today because we are going to get into some more complicated examples of composing these kinds of functions with unlike functions like cosine with sine, etc. So this is a good stopping place for today. You definitely now have the information you need to do intro inverse functions in ALEX. So whenever you get a chance, get started on that. I will make sure to release your exam grades by class tomorrow, as well as put in your grades for Unit 2 ALEX topics and your knowledge checks. So by the end of the day, you should have a really good understanding of where your grade is, where you're at in the class, and to do some evaluation of how am I doing. All right.